Okay, so now we're going to do this example. Consider the region bounded by y equals 2 cosine x, y equals 0, x equals pi over 6, and x equals pi over 2. And the question is, what is the volume of the solid if we rotate this about the y-axis? Okay? So now, let me draw the figure for you here. Okay? I know that if I look at the y-axis, like if I look at the y-axis and the x-axis like this, I know that the 2 cosine will look like this, right? Here at theta equals 0, 2 times cosine will be 2, okay? So this is 2. And here at pi over 2, cosine is 0, so 2 times cosine 0 is 0, so it'll touch there. I already have my pi over 2 boundary here, right? Pi over 6 is somewhere over here, you see? So I can see that this part in here will be the region. Y equals 0 is the x-axis, right? And of course y equals 2 cosine x is the top. So now when I look at it like that, I can see, I can delete this part over here, right? And I'm left with this region R like this. Okay? And now here, in this problem, we're going to rotate this about the y-axis like this, okay? Okay? This is my y-axis, of course. This is my x-axis. So if I'm going to rotate it about the y-axis, what do I want to do? Now, strictly speaking, there are some of you who might say that we could use the disk method. And that is totally true, except that would require us to find out this length for each of these, for the y values, okay? But we're not going to do that today. The easiest technique in this case is to use the cylindrical shells method. Because if you notice, from the y-axis to any x value in this region, and this region goes from pi over 6 to pi over 2, I can see that that radius to the axis of rotation is nothing but the x value, okay? I also see that the height of the sheet that would be in the cylindrical shell, or that would make the wall of the cylindrical shell, is just the y equals 2 cosine x value itself. So I can see that if I write my formula, okay, my volume is going to be the integral, from a to b of 2 times pi times r of x, where of course r of x is, for any x value in the region, it is the radius, it is the length of the radius to the axis of rotation. In this case, it'll just be x, again, because we're rotating about the x-axis. The f of x will be the height of the sheet that will compose the cylindrical shell, dx. And what we just discussed here is that the r of x, in our case here, will be simply x, because we're rotating it about the y-axis. The f of x is going to be the height, which is y equals 2 cosine x. And so we are prepared, and of course the lower limit and the upper limit are the pi over 6 and the pi over 2 respectively, as we go from left to right on this figure. So let me write this integral for us, okay? So the volume will be given by the integral. I can pull the 2 pi out to the front already. So it'll be 2 pi. Let me write this nicely, I'm sorry. So this will be given by 2 pi times the integral from pi over 6 to pi over 2 times the r of x, which is x, times the f of x, which is 2 times the cosine of x, okay? And that with respect, of course, to x in this case. Now, this 2, it's just a constant. I can pull it out of the integral, and I can see that this can be written as 4 times pi times the integral from pi over 6 to pi over 2 times x cosine x dx, okay? And so then I'm going to calculate this integral, right? So we're going to calculate this integral, okay? So the first thing that you might observe here is that you have a product of two functions, okay? In some cases, the product of two functions is easy to integrate because the functions combine in a way that makes the product very easy to calculate. Let me show you what I mean here. Like, let's say we were going to integrate x times 5 minus x squared dx, right? Then I could perform the FOIL method on this 5 minus x squared, and I would get that this would be the same thing as the integral of x times 25 minus 5x minus 5x plus x squared. And of course I could combine these two like terms, then I could distribute the x inside. Okay, so I would get integral of x times 25 minus 10x plus x squared dx, and then I would get the integral of 25x minus 10x squared plus x cubed dx, right? By distributing the x inside. And then I would use the power rule to take the integral of each of these. And then, of course, I know that the integral of a sum is the sum of the integrals. So I would add up those integrals and I would get the result. So I wouldn't need to use any fancy techniques, or not fancy techniques, but I wouldn't have to use integration by parts or substitution or things like that. But as you can tell from this example, this is not one of these cases. Here, we're actually going to use the integration by parts. And this is partially why I designed this problem, so that we would have an opportunity to see the integration by parts. By the way, I know I didn't do this example that I just showed you here in full explicit detail, but I just wanted to show you enough so you could see how when you have the product of two functions, the integration by parts is not always necessary, but that in certain cases it is necessary, as we can see in this example. Okay. Okay, so the way I want you to think about it is like this. Okay, the integration by parts formula says that you have the integral of f prime g equals f times g minus integral of f g prime. The critical thing to realize and to remember is that whatever function is has the derivative being taken on the left hand side, it has to be the opposite function getting the derivative taken on the right hand side. Notice how here the f is primed, we're taking the derivative of f, and here the g is primed. Okay? Okay. Now one of the things I like to always tell my clients, one of the things I always like to tell my students is that the motivation for, well, not the motivation, but whenever you're going to do an integration by parts, I always want them to make a table over here. Once they've written the formula in general, this is the way I do it myself. I write the formula first, and then I tell all my students and all my clients to write down what's going to be your f, what's going to be your g. Why? Because we need to make sure that this second integral is going to be in some way easier than this integral. Okay? Okay. So if you look at this, look at this. If I were to take the derivative of x, that would make the integral easier. So if somehow g was x, then g prime would be 1. And so this integral would be easier. So with that in mind, let's do that. So g is going to equal to x. Okay? And then that forces my g prime to equal 1. But that means that my f prime has to be whatever is left over. In this case, cosine x. Right? So my f prime is equal to cosine of x. And so then we ask ourselves, is there a function whose derivative is cosine of x? Sine of x, right? So that means that my f over there is going to be sine of x. Okay? So what you can see now is, using this setup, okay, I can evaluate my integral. Okay? So I can say, this is going to equal my fg. Okay, let me make a quick note here before we can proceed. Because here, notice this is not an indefinite integral. There I wrote it as an indefinite. Here it's a definite integral. So, by the way, so what I could do is I could calculate the indefinite integral, and at the very end, plug in the upper limit, and then subtract with the lower limit plugged in. Okay? Or, which is what I'm going to do here, I'm going to use the following modification. It's not a real significant modification, but basically the integral from a to b of f prime g is going to be fg evaluated from a to b minus the definite integral evaluated from A to B of fg prime. Okay, so that's the way we're going to do it here, but you could do it either way. So now here, this is going to be equal to, first of all, fg. What is my f? Sine x. What's my g? X. So it's going to be x sine x evaluated from pi over 6 to pi over 2. Okay? Then look at this. Minus, so I put my minus sign. Okay? And then, how do you call it? And then it's going to be the integral of f times g prime. Aha! It'll be the integral from pi over 6 to pi over 2 of, again, f times g prime, which is sine of x times 1, which is just the sine of x dx. You see? By the way, I just put this open parentheses as a way of me indicating that this expression in this parenthesis and behind this line is the integrand that we're going to evaluate at the upper and lower limits. Okay? So now I'm going to bring this down as is. We'll evaluate at the end. Okay? And then I want to ask myself, I'm going to integrate the sine of x dx. So the way I want to think about it is this. So I'm going to put my minus sign from here, and I'm going to say, okay, what is the integral of sine? Is there a function whose derivative is sine? Well, I know that the cosine has derivative negative sine, right? So I'm going to have the negative cosine here. Because if I take the derivative of the negative cosine, then I'm going to get the positive sign. Okay? And I'm going to evaluate that from pi over 6 to pi over 2. Okay? So now, as you can see, I have transformed this integral using the integration by parts formula into this integral, or into this difference of integrals. And now finally I've evaluated both of the integrals. Well, okay, you guys know what I mean here. The first came out already evaluated, and the second one I've evaluated here already. Okay? Okay. So now we can start plugging in. Let's look at this one here. This is going to be, I'm going to evaluate it at pi over 2. So pi over 2 times the sine of pi over 2 minus the pi over 6 times the sine of pi over 6. Okay? And then minus, and then here, okay, it'll be negative cosine of pi over 2 minus, and then this is negative, so it'll become plus cosine of pi over 6. Now, by the way, it is also true that I could have pulled out, in this case, I could have pulled the minus out, made this into a plus, and then evaluated it like that. But the key issue with this is just that you have to be extremely mindful of where the positives and negatives are. Okay? Okay. So now here, we have to figure out what these values are. Luckily for all of you, I have my magical unit circle here before me. And first of all, the sine of pi over 2, this one you should all know by heart. You should know that it's 1, because the y value of the unit circle at pi over 2 is 1. So this will simplify 2, open bracket, pi over 2 times 1, that's just pi over 2, minus, at pi over 6. At pi over 6, the sine is 1/2. So it's going to be pi over 6 times 1/2. Okay? Right? This pi over 6 times the 1/2. Now, minus, okay, open bracket, cosine of pi over 2. At pi over 2, the cosine is the x-coordinate of the unit circle, and in this case, you can see that that's clearly 0. And what's the negative of 0? Well, the negative of 0 is just 0. Then plus, what's the cosine of pi over 6? I go to pi over 6, the cosine is square root of 3 over 2. So it's going to be the square root of 3 over 2, like this. Okay? Okay. Let me put this over here. Okay, perfect. Okay. So then here, I can start combining everything. What is pi over 2 minus, you can see this is going to become pi over 12, right? So pi over 2 minus pi over 12, and then minus square root of 3 over 2. I'm going to put them all over 12 as the common denominator. To do that, I'm going to multiply this first fraction by 6 over 6 and this last fraction by 6 over 6. And so you're going to see here, this first fraction, or this first product, is going to become 6 pi over 12 minus pi over 12 minus, and then 6 times the square root of 3, we just leave it as such, 6 times the square root of 3, and then 6 times 2 is, of course, 12. So now look at the top. Now, whenever I'm adding or subtracting fractions when they're on the same denominator, I just add or subtract the numerators and keep the denominator. So I can say, what's 6 pi minus pi? That's 5 pi, and then minus 6 square root of 3. So it's 5 pi minus 6 square root of 3, all of that over 12. Okay. So this finally is the value of this integral when we have taken it all the way to the end. Okay. Okay. And let me just notate something over here on this side that I kind of used here but didn't make explicit, but that I do want you guys to have explicitly seared in your brain, and that is that the integral of the sine of x dx is equal to the negative cosine of x plus some integration constant. It's very useful to know this formula, and also the other one that's very useful to know, although we didn't even use it here at all, is that the integral of the cosine of x dx is equal to the sine of x plus the integration constant c. Okay, and the way you can always test it is, what's the derivative of the sine of x plus c? Cosine of x. Remember that the derivative of the constant is 0, so this expression on the right, the derivative is just the cosine of x. And what's the derivative of the negative cosine of x plus c? Sine of x. Okay. Okay. In any case, we can see that this integral gives us the value 5 pi minus 6 square root of 3 over 12. Okay. Okay. And so now what we see is that this is going to equal to 4 pi, open parentheses, 5 pi minus 6 square root of 3 over 12. Okay? Like this. And now I can distribute the, well, I don't have to distribute the pi. I could leave the answer like this. Strictly speaking, in my opinion, I think we should distribute the 4, or at least we should pull out a factor of 4 from the bottom to cancel out with the 4 in the front. And then we could leave the pi on the outside or distribute it, either way. So in my case, for my own taste, if I cancel out the 4 on the top with the 4 and the 12, I'm going to be left with pi times, open bracket, 5 pi minus 6 square root of 3 over 3, like this. Okay? Whoa, that looks like it's a cube there. That's a square root of 3. Sorry. Perfect. And so there we have it. That's the volume of the figure. Okay? Okay. And so let's proceed to another example.